Hello everyone. Hope everything working fine now. Today we are going to solve today's daily LeetCode problem. You can find it here. Uh, let's see what is the problem today. The problem number is 3660 jump game 9. Okay. So what the problem statement says that you are given an integer array nums from any index I. You can jump to other another index j under the following rules. Okay. Jump to index j where j greater than I and is allowed only if nums j is less than nums I. Okay, that means if you can jump in the right if the value is less than current value, and similarly you can select any index j where j is less than I and nums of j greater than nums of I. Okay, for each index I find the maximum value in nums that can be reached by the following any sequence of valid jumps straight at I. Return an array answer where answer I is the maximum value. Okay, so let's see the example here. Here the example is 213. So let's go to the here. Like we have 213. So from 1 second, like from 2, we can jump in the right direction if the value is lesser. So first we can jump here and then this the only jump possible. So from 2 we can go up to like maximum value we can reach each 2, from 1 also each 2, and here is 3. So that's why the answer is here 2 to 3. In this case for 231, like for 231 if you see carefully, 231, from 2 we can jump to 1, and from 3 we can jump 1. So from every one we can go like reach to 3. So for all the answer will be 3. So basically, if you see the problem, like it looks like kind of we have to find how many like connected components are there. Like if you see in the graph manner, like these are the each indices is a node, and there is a edge if the condition holds. Like if the left value is greater than the right value, and after that we have to just find the all the connected components, and for each value in that connected component, the answer will be the maximum value which is in that component. So, like here, if we see carefully, like in this example, from 5 we can jump to 1, from 10 we can jump to 8 and 1, from 8 we can jump to 1, from 11 you can jump to 10, from 13 jump to 10 and 12. From 12 you can jump to 10. From 17 you can jump. So here basically we have two connected components. One is this and another is this. So for all of the value in this component, the answer will be the maximum of this component, which is 10. This is 10. All will be 10. And for this, the maximum is 17. So answer will be 17, because as this is a connected component, so we can from every node we can reach to 17. Like there is a path. So how we can solve this problem? Like if we do in the brute force manner, like from each one we just connect and like an edge, and then after that we go to like find the connected component. Then there might be like in square kind of edge. Like if the graph is kind of like decreasing, like 10, then 9, then 8, then 7, then 6. Then from each node we can reach from everyone. Like from 10 we can go to each and every one. From 9 we can go each and every one. From 8 similar to we can go everyone. From 7 we can go. So you can see like from this we can go n minus 1 nodes. Like for 10 there will be n minus 1 edges. For these n minus 2, n minus 3. So it will be quadratic time complexity. So it won't work. Like we have to find any optimized approach. So for that, like if I try to find an intuition, like let's say first of all we are find the maximum value in this array. So here it is 17. So as the 17 is the maximum in this array, so all values after 17 will be definitely like less than this because this is the maximum value. So all values can be reached from here. Like we can jump all of them from the right of this. Like if there are also another value like 15 or something, so we can go like jump to 15 from here. So this will be a connected component. And then for these part, let's say the max, let's say we are finding the maximum of this part again. So in this part, the maximum is 13. So for this, we can reach here uh, all the values right to it. But if you see carefully, we can reach also to this component. Like here, the minimum is 10. So from 13, we can reach to 10. And now this whole thing becomes a single component. Similarly, for this, here is like the 11 is maximum, and we can reach here. We can reach 10 from 11. So this will be again a connected component. And now here the 10 is maximum. So from 10, like we can reach all the values right to it. And if we see in this connected component, the minimum value is 10, but from 10 we can't reach here because we have to get anything lesser than 10. So we won't be able to go here. So this will be a connected component. And for this 5, if you see here, the as there is 1, so we can reach here. So this will become a connected component. So if you see carefully, the connected component will be contiguous. Like from these to this is a component, from these to this is a component. So there won't be like discontiguous component. Like it won't happen that this is a component and this is a component and there is a path between them and another component lies between them. It won't happen. Why it won't happen? Like in this case, as there is a path, so let's say there is a element 8 is there. So let's say any value x is there. So here we must have like a value which is lesser than this. So this will be let's say 5 or something. So in this case, like it is not connected to this or this component. Like for contrary, we just assumed that this is not connected to any one of these. That means there's the all of the values here are less than 5. All of the values are less than 5 here, like for any x, because less or equal to, like if any value becomes like greater than 5, then there will be a edge. And for similarly here, no value will be like no value will be less than 8. So every value will be greater than 8. So one second, uh, like here, as there is no edge with this component, what does that mean? That mean every value is less or equal to 5. So for all x, like for all x is less or equal to 5 here. And for this first component, if we see, for this first component, every value is greater or equal to 8. Because if any value is less than 8, then there will be a edge. So for second case, we find that every value is greater or equal to 8. Like, so if you see, all values are less equal to 5 and also in the same time greater or equal to 8, which is like not possible. So this won't happen anytime that between two connected components there is a independent component there. So there will be always a single connected component, like contiguous connected component will be there. And So when there will be two component which will not connected, like if you see carefully, like this component and this component, like if there is a partition, that means no edge from this left to go to right. That means the minimum of this right have to be, like if we take the maximum here, it have to be less than or equal to this minimum. So in this case only there will be no edge, because the maximum value here is less than the minimum of here. So there will be no value which will, like, greater than this. So there will be, then there will be no edge. So what will be our idea? Our idea will be, we will first calculate the prefix max for the array. Then we will came from this back side and we will just check that if this can be a pivot. Like when this will be a pivot, if the minimum of this whole part is greater or equal to this prefix, like maximum of this left side, then there will be a pivot. Pivot means barrier, so there will be no edge. So this side will be a single connected component. So if I dry run this approach here, so if I see like if pivot can, like barrier can be here, like then the maximum of this value have to be less than this minimum of this. The maximum of this is like 13 17, which is not less than 15. So this won't be pivot. Here also the same, here also the same, like the maximum here is like if I draw a barrier here, the maximum here is 13 and the minimum here is 10. So again there will be a edge from here to here. So there won't be a barrier. And similarly, like here will be a barrier. Like where if you see the maximum here is 10 and the minimum here is 10 also. So there will be no edge passing through this component to this. So let's code this approach. Like what we will do, we'll first calculate all the prefix maximum to query the left side maximum in order of one time. And also we will maintain a suffix minimum, that what is the minimum value we have encountered so far. And we will just check that if this minimum here is greater than the maximum of this left side, that means there is a barrier. Means there will be no edge from the left to right. So these two will be disjoint segments. So after that, we will just, for each segment, we will calculate the maximum of this segment, and for all of the value, the answer will be that. So here in the editor, first like rename this to array, then we will just calculate the size, and then we will take a, like, create a prefix here, prefix of n, like this will be a prefix max. So now prefix max of 0 is basically simply the array of 0. Like the definition of prefix max of I is like the maximum from, so basically prefix max of I is denote that the maximum element between 0 to I, like the maximum element from indexes 0 to I. And now for int I equal to 1, um, I just put in I plus plus, prefix max of I equal to simply maximum of prefix max of I minus 1, comma current value. So we have created the prefix array here, prefix max array. So prefix max of I, prefix max of I minus 1 mean the maximum up to I minus 1 and the current value. So after that, we will just came from the back side I equal to n minus 1. Then I will be greater than 0. Uh, Greater equal to 0, I minus minus. We will store a suffix minimum. So we will store a suffix minimum here. Let's initialize with a large value. So the value can go up to 10 to the power 9. So let's initialize with 10 to the power 9. Then we will just minimum this, like suffix minimum equal to minimum of suffix min comma current value. Now we have to just check that if this suffix minimum is greater or equal to the prefix max, up to I minus 1. So in this case, there will be a barrier. In this case, there is a barrier in between I minus 1 comma I. Like there will be no edges coming from like left side of I to right side of I including. So we have to store the segments. So we will just store the segments. Vector, let's take a pair of int. These are segments. So segments dot we will just push back. So I each current left pointer, like from here we need to take a right pointer also, like which will denote up to which the component exists. So initially let's take it in. So the right pointer is basically excluded, means if this segment is from uh, left to right, then the right is excluded here. The segment is from left to right, and the right is excluded, means right is not included in the segment. So we will just, or we can implicit back. So current is I and right, and after that we will just update right to I, because if there is a barrier between I minus 1 and I, then for the next range, like the next contiguous segment, the segment will exist up to I minus 1, and here the right is excluded. So we will just capture this I because I is not included. So this will be this. So now we got all the segments, and in last we will just place back this 0 comma left right, because we have to lastly we have to place the first segment also. And now we got all the segments. Like if we print the segments, you will get to know like what is happening. Left and right. Just we just have to return a vector. So vector answer of n, and we will just return answer. Now we are just returning answer with all zeros. We are just printing to see that what it stores in the range. What happens? Okay, we are going up to 0 here, but we are accessing I minus 1, so that's the issue. So we have to go up to 1. And here you can see there, like for the first one, we know the segments are one component is 2 1, which is 0 to 2, and then there is this 3, so which is 2 to 3. So 0 to 2 mean 2 is not included. So 0, 1 is a segment. And next 2 to 3 means 3 is not included. So 2, 2 means only the 2 index is a. And for the second case, you can see the only one segment, like one component exists, which is 0 to 3 means 0, 1, 2. So we are calculating all the segments correctly. So now what we have to do, we have to just process all the segment one by one, and then we will find the maximum of this component, because from all the nodes of this component we can reach to the maximum node. So we will just calculate the maximum of this component, and we will fill the answer for all of the values in that component with that maximum value. So let's comment this out and let's find the maximum here. Uh, like the component max is basically nothing but max element. You can find like from go up to left to right, or you can use HTL function. So I'm using it. Maximum element from array begin plus left to array begin plus right. Here from this function also takes two iterator. One is included and one is excluded. So we are giving it rightly because we the right is excluded here. So after that we will just simply fill the answer dot begin plus left comma answer dot end plus right with this component max. And if I run this should work good. Answer dot begin answer dot, okay. So here also we have to begin. Mm, yeah, it got passed on the samples. Let's run this on the main case to see if everything good or not. Yeah, it got accepted. So this was the approach like you can take. If you look at the time complexity, like here we are just uh, traversing the array once, and here also we are traversing it once. So and here also like the component in the worst case also can be like go up to n, and as we are accessing each component only once, so this will be also linear. So the time complexity will be overall linear. So here if I see the time complexity is basically order of n, and the space complexity is also order of n, because we are uh, we are creating this prefix max and also this segment vector. So this was the approach. Like you can also think the other approaches, like you can also think this in the monotonic stack way. Like if you see here carefully, like uh, the value are kind of growing monotonously. Means let's say initially 5 is a component, now you got 10. So as the 10 is greater than 5, that means it won't connect with this 5. Now we got 8. 8 is like not greater than, sorry, not less than 5, but it is less than 10. So 8 will merge with this 10, because there will be a like connection between them. So these two will be a component, and for this the maximum value will be 10. So in this component, like 10 is the leader kind of. Now there is 1. So 1 will connect with 10 as well as 5. So it will go here and also connect here. So that means this total will be a component where the maximum element is 10. So 10 is a leader. Now here we got 11. So 11 won't connect with this because the leader is less than this. Now here is 13. 13 will connect with this because and in this way, like you have to just take a stack and then you have to track like the boundary and the maximum value of this component. If the current value is like less than this, means there may be a connection between them. You will just simply merge those component and update the boundary, and in that way you will find the segments also, and after that finding the component you can calculate the maximum in this component. So that is also a solution. In the monotonic stack also you can, like, the time complexity and space complexity will be the same because the idea is same here. So that's all for today. Like, let me know in the comment, like, which other approach also you would take to solve this problem, or like what thought came fastly into your mind after seeing this. So that's all for today. Thank you.